Any questions from last day's classes? Everyone has access to all the material, right? Because I have the in the course plan sheet on the very first sheet where you have the references. I have added a few more references. The last class I was talking about the concept of Z numbers to represent belief networks. So the paper on Z numbers is there on the sheet. And secondly, is today I'll be talking about semantic networks. And there is a paper on semantic networks, which is a beautiful summary of the entire concept of semantic networks. So I have put that on on that sheet as well. Okay, so yeah. So do take a look at it and let me know if you have any questions. So the concept of Z mouses and Z numbers are in the same paper. Okay, so yeah, and anything else? No. So any questions? Okay. If not, then now, since the last class we were talking about knowledge representation, which is all about representation of all the facts that we know, facts and their instances, right? And these facts could be deliberative in nature, they could be procedural in nature, they could be derived through a sequence of inferences. They can have belief values, they can have confidence values. You can use different kinds of mathematical techniques to derive belief values. These knowledge representation formats that you'll be using, they need to be dynamic in nature, right? So these are things that we have been discussing in the last class. So in today's class, the first thing that I would like to show you is a beautiful example of what an activated semantic network looks like. Okay, let me show you. Let me share my screen. Here. Do you see this page that calls it a thought bubble? Do you see a picture? Hmm. So now, yeah, so this is a beautiful example of what an activated semantic network looks like. What I mean by activated semantic network is that you have received certain sensory stimuli and then different sections of your knowledge base are now active and bringing in facts and figures into your working memory, right? So now see this dotted thing that you see over here beside the picture, we can assume that to be a human being. So this human being looks at the picture and this is everything that comes to the person's mind. Could be the name of the artist, then the name of the style, and because they have very similar auditory factors, then you have Barack coming over. From Barack, you have Bark, Bark reminding you of a dog, so you have a poodle, and then you have different names. You have Monte Carlo, you have colors, red, green. Somewhere there's Mickey Mouse also written over here. Donald Duck. Okay, so what happens is in in the context of one thing becoming active or one concept becoming active, because of its other sensory information attached to it, or maybe because of its co-occurrence frequency with some other context is very high. So you have this entire network getting activated, one point after the other. Okay, so this entire bubble that you see over here is an example of what our brains actually get to when you receive certain stimuli. So obviously certain questions that are very important over here is, for how long do you allow this thought bubble to be active? How for how long will you allow all the thoughts in the thought bubble to be active? When are you going to prune away something from your working memory? Right, so these are certain very fundamental questions that are important. Right, so this is a very interesting picture. It came out in the New Yorker in 1969 and it's called a thought bubble. Okay, you see colors, you see shapes, you see different kinds of multimodal representations within your brain getting activated because of a certain sensory stimuli pattern. So this is a very beautiful example. And now I'll go on to the class notes.
Ma'am,
Hmm, hmm,
yeah. In this thought bubble, I want
yeah,
to know one thing.
yeah, yeah.
Well, the thought bubble could be a different for the very different person, right?
Absolutely,
And
absolutely.
and the kind of the sensory organ we have will
Hmm,
recognize them something and analyze the something in a different pattern
hmm,
according to their past experience. That is how
absolutely.
the human brain works. But
Exactly.
in this case, like, are we completely able to represent this in the form of like what you have shown in the picture, or are we missing something?
So we are missing a lot of it because we still do not know the kind of data structures that we need in order to be able to do this kind of an activation. We are still trying to design data structures.
Okay,
We have,
so this
yeah,
could be, yeah. So this
this
could
is
be,
the
might
ultimate
be like,
thing. This is the
okay,
goal.
okay,
This is the kind
okay.
of goal that we want to achieve. Okay. And this is like kind of giving you what you want to have your AI system do.
So like it is not generalistic. Instead, it is something specific to the person. As
Yes, it is generalized in the sense of the bigger context. Generalized in the sense of the bigger context, meaning you start with a picture and you end with Donald Duck. Okay, so you have multiple things getting activated. So across different sections of the semantic network, you have activations happening. But what memory gets activated is specific to the person. Hmm. And the generalization that I said, it is in relation to the knowledge base of that person. Okay, and specific memories in relation to that person. So what you said is correct. So if you are trying to build a dynamic embodied AI system, then you might have to think about all of this. In the last class also, I was talking about qualitative and
yeah, yeah, yeah.
quantitative.
So
Yeah,
yeah. So ma'am, in continuation of Sam, that's what I
yeah.
want to know.
Hmm.
Well, will it be really possible to like capture those diversity in a particular embodied AI? Is it possible to consider all the scenarios, or there will be always some limitation to that?
See, we all have limitations. You and I, we cannot activate everything in our brains, can we? So there is
Okay.
always going to be a
Hmm.
limitation. Right,
Got it.
but now there is a famous paper that says that at any point in time we can process a maximum of seven things. The human brain. We are
Sorry,
active,
sorry. Come again, ma'am. I missed it.
yeah,
Maximum of seven things.
seven things at a time.
Okay.
And that is the cognitive limitation generally that we have. That is seven things. We process four things best, and after seven things, it starts waning. So if you have seven things being bombarded at you, you will be able to process it. But if it's more than seven, you tend to ignore a few things. Okay, but if it is four, you are equally responsive to all of them. So this is a paper that talks about it. But now when it comes to our computing systems, it could be possible that the processing power is a little higher, right? Because in the brain, we have very limited neurons and everything, right? We do not have unlimited GPU power. But in our current computing systems, we have a lot of GPU power in hand. Right, so the number crunching facility is a little bigger in our current day processing systems. So this seven could actually be a little higher. So here there is a philosophical question that do we need it to be bigger than seven or not? That is a debatable question. But for human beings, it is pretty much around four to seven. But for current processing systems, it is higher because of the compute facilities that are available. But despite all the computing facilities, we are still not able to generate a thought bubble as beautiful as this. Because of uh, the the lack of understanding of what kind of multimodal activations work in the brain. Let me give you an example. When I talk to you about, I've talked to you about this before also. Say you go for a holiday and you have a bowl of pumpkin soup in that holiday. So whenever I'm going to talk to you about say a fresh bowl of pumpkin soup, it is highly possible that that memory of the trip also becomes active. Why? Because that somatic factor or the emotional value of that trip is very high. And that particular bowl of soup that you had in the trip was very good. So now, when you recollect this memory, the different sensory organs that are in sync with that memory are also activated. So when you remember pumpkin soup, you have a sense of smell, you have a sense of taste, and you have a sense of vision of that pumpkin soup also getting activated. Okay, so this is what fMRI studies have told us, that when you recollect a memory, its sensory organs are also activated to kind of help you relive that memory. Okay, so these are certain questions that we are yet trying to design, we are trying to work on it. At the moment, we are able to work with two multisensory modalities, but attaching a somatic factor to memories and accordingly getting things activated, that is still a question that we have to contend. Hmm. So, yeah, does that answer your question?
Yes, ma'am.
Hmm.
I got. Thank you so much.
Yeah, fine. So now I'll move on a bit. So this is something. Wait, let me change my screen. Hmm. So now we're going to talk about semantic networks. So semantic networks, like in the last class, we talked about predicate logic, which is about writing logical statements to connect facts based on certain features. So now a graphical representation of that kind of a logical network is what is a semantic network. Okay, so what we have is here are nodes connected by edges. The nodes could represent actual objects, they could represent concepts, they could represent facts, they could represent anything. Okay, so you have nodes and you have edges which connect these two nodes based on certain features, a kind of a relation. For example, part of is a kind of, belongs to, a subset of, color of, has, verbs. So you can have nouns, adjectives, verbs. You can have all of that actually helping you um, kind of label these edges between two nodes. Okay. So now the question is, these object frames that we have, they are usually the common data structure that we use for representing objects are called frames. So if you remember from Marvin Minsky's session that I had on Society of Mind, there also we talked about frames. So frames are essentially data structures that show you instantiation of certain attributes. Okay, so when you have an active semantic network, meaning a part of your knowledge base is now active given a time t, so what you have is a network of these kinds of frames getting activated. Hmm. So frames over here, you have attribute and values. Okay, and this is, for example, this is in sync with object 1, this is in sync with object 2, this is in sync with object 3. So in the basic semantic network, you have a representation of object 1 being associated with object 2, object 3, and object 4. And given certain input, you have the frames of that semantic network getting activated. Okay, so frames are like instantiations of objects within a semantic network. So when you are trying to design a semantic network for your use case or for your problem, a frame is a basic data structure that you can think about. So now there are certain limitations when it comes to frames because they are pretty much, the representations that we have at the moment are pretty text based, text heavy. So you can think about multimodal frames also, where you have actually a signature. Say this is a sensory signature that you have, and this instantiates a frame. What do I mean by sensory signature? It's like, for example, I'm holding a pen. It has certain sensory components which activate the pen memory in my brain. Okay, so this signature that it has to be long, it has to have a pointed edge, it needs to write in this fashion, it needs to feel like this. So this kind of sensory stimuli is a signature that kind of activates the pen frame in my brain. Okay, so you can think about multimodal frames also depending upon your use case. So now the basic kinds of knowledge representation components that exist in a semantic network are logical representations, obviously, facts and how they are connected. And then we have, no, sorry, my mistake. The basic knowledge representation types that we have are logical representations, what we did in the last class, semantic networks, just like I told you. Then we have prediction rules. Prediction rules are a part of both logical representations and semantic networks. What are production rules? Meaning, if then else statements, how are these facts going to be connected? What threshold will lead to what kind of activation? Okay, so you cannot have your entire knowledge base getting activated, right? It's only subsets that have to be activated. So how are these subsets going to be activated and what are you going to do about them? So that is what production rules say. And then we have frames, just like I told you. So when it comes to designing frames, at the moment you are free to design the kind of data structure you want. It's just a terminology that is called frames. Okay, so you have slots and values, an attribute and a value attached to it. Fine. So now there are different kinds of semantic networks. One is a definitional network. A definitional network is like a hierarchical network. What is like a hierarchical network meaning? Um, Say you have animal, then you have mammal, then you have maybe two-legged, four-legged, under four-legged, and so on. Okay, so when you have a semantic network that talks about a hierarchical structure of generalization to specialization, that is when you have a definitional network. Okay, because it is giving you the broader picture of a certain concept or the broader definitional perspective of a certain concept. After that is what we have is assertional networks. Assertional networks, say if uh, these are like activations of certain instances of an object. Okay, so when I talk about a definitional network like this, an assertional network would be like, for example, uh, animal, mammal, four-legged, dog, tin. Okay, so now what is happening is given the certain input that we have, this definitional network got connected to a certain fact or a certain instantiation of the object dog, which is Tim. So Tim is a dog, and now Tim inherits all the features that are there in the definitional network attached to dog. Okay, so when we have Tim getting activated, that is when you have an assertional network getting activated, because now what is happening is Tim is going to be fed or activated with all features that exist in the dog semantic network. Okay, so definitional is more about concepts, and assertional is when you instantiate objects given properties of that context or that concept. Okay, then we have implicational networks. Implicational networks are these kind of define a transitive relationship from one object to another object. Like if A leads to B, B leads to C, then you can infer that A is going to lead to C. Then you also have belief networks. Belief networks meaning that if remember, like I had told you, if I have values like this, that A knows P, so then you can attach a confidence factor to it, meaning A knows P with what kind of a confidence value. So if my network is essentially talking about how facts are connected and how inferences are going to come because of a top-down approach, or if I talk about belief values within my network, I am moving towards an implicational network. Hmm. Executable networks are all about connected procedural knowledge modules. Like if I pick up a pen, then I'm going to do this, I'm going to do activity A, I'm going to do activity B. So if I lift it up, if this object is heavy, if this object is light, what kind of procedures are going to be activated? So in a network, you, excuse me, someone has come. Excuse me. I'm so sorry. In every class, it seems like someone comes, isn't it? Okay, so what was I talking about? Um, uh, Executable networks, yes. So when you have a certain sensory stimuli activating a part of your semantic network or part of your knowledge base, what is getting active are activity responses. Okay, so when you have procedures getting activated in relation to an input, if you have a network that is designed like that, that is what you have is a procedural network or an executable network. Now, if you make your network dynamic, meaning that it keeps updating itself, it has rules associated with updating itself. Through updating, I mean pruning, adding new facts, correcting new facts, belief revision. If you have that kind of a system built within your semantic network, that is when you have a learning network because it is dynamic. Okay, it is not just fixed to what it has been trained with, but you are making sure that it lives in the world. So you have a learning network. And hybrid networks are combination of two or more such networks. Okay. So now, given the different projects that you are working on, can you give me examples of what kind of networks you are working with? What kind of such activation things you are working with? Yes. Hmm.
Can you repeat the question? I'm sorry.
My question is, given the projects that you are working on, what kind of semantic networks do you think would be applicable to your project? Definitional, assertional, or a hybrid network? What have you designed or what are you planning to decide? Yes, if you
I
can
have
share.
implemented HTN,
What is that?
hierarchical task network.
Okay, okay. So what category would you keep that?
It should be definitional only, right?
Hmm. It's entirely definitional. Are you sure?
No, because I have given some examples as well under
Hmm.
this. So it must be under that assertional network only.
So it will be definitional, assertional, as well as executable, isn't it?
Yeah, 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 right.
Because you have task functions also
Hmm.
associated with it.
Right.
So it is a hybrid network of all of this. Right. So what I would suggest all of you is that when you are looking at your project, when you're looking at the kind of knowledge base or the kind of semantic network that you are trying to design for your base, for your project, make sure that you look at each of these elements also. Okay, and if you're actually implementing it, if you are able to code it, then you can give us a demo of how these activations are happening. Okay, whether at the definitional stage or whether you have actually moved on to procedural networks, talk about it. Okay,
So, ma'am, will there be any presentation, or you are looking for any
no, no.
recorded demo for it?
You can submit a demo as part of the zip folder.
Okay.
You can
Is
do
it a
that.
optional or kind of a mandatory?
No,
You
no,
are
no. If you do a coding, if
okay.
you do coding, you get bonus 5 points.
Okay. Okay.
Okay, otherwise it's going to be a theoretical exercise.
Okay.
Means if this semester section had been a little longer, then we would have taken project vivas. We would have done that, but we unfortunately don't have that time.
So, ma'am, what I understood from this is like even though we try to coding, but we also need some physical simulation to
Hmm.
represent it, right?
Hmm, hmm,
So,
hmm.
how will that possible?
So you can take up certain use cases. So when you're coding, say you're coding the knowledge base and you're coding rules and everything. So you take and say hard coded signatures of certain sensory stimuli. Take in a code like that. You don't have sensors, so take in
Mhm.
a code. Okay, take in a signature input from the user and then show how
Okay.
the activation is happening. Show how an activity is moving from step 1 to step 10. Show that.
Okay. 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 Got it.
Hmm. Since we are not dealing with proper sensors that are going to take in information from the real world, we can just hard code a signature. Hmm.
Got it. Yeah.
Yeah. So here I'd like to talk. This reminds me of something which is called afferent. Afferent and efferent data. What is afferent data? Afferent data is what you receive from the external world and what it activates. And efferent is in the other direction. This is brain activations. It's like you have the real world and this is your brain. So you have afferent inputs and then you have activations in the brain which lead to efferent signals, which are like responses. Okay, so here what we have, what I'm talking about is when you receive certain sensory stimuli, there are many things that you have to think about over here. The first thing is, the first thing is how big is your packet going to be? By packet, what I mean is for how many milliseconds are you actually going to collect sensory information to form an entire packet, which will then be an input to your system. Okay, what I mean over here is when you look at something, are you going to wait for 1 millisecond worth of data or 2 millisecond worth of data to be collected and then be processed as part of your visual stimuli? Okay, so for how long are you going to form that packet? For how long are you going to actually collect that sensory stimuli to be interpreted later on? So now over here, this packet is somewhat um, it is there is a generic packet, like you look at something for 2 milliseconds and you process the data and then you again respond to it. By responses, I mean it could meaning dilation of your pupil so that you collect more information, so that the packet that you actually collect from the environment is a lot more feature heavy. Okay, so maybe you are collecting 2 millisecond worth of data after an attention procedure has been alerted. You are collecting 2 millisecond worth of data, but maybe the features are getting more activated. Like say in the initial packet, you had 5 features, but now in the second iteration, when you are paying more attention to it because of your pupil dilation, you are collecting more information. Maybe now you have 10 features getting activated. Okay, so what we can consider this is to be like in one way, which you can visualize is you have this big placeholder. This is for feature 1, this is for feature 2, and this is for feature n. At any point, at any time t, a subset of these features are getting activated. And that is the packet that you are processing for the efferent signal responses to that input. Okay, so we can visualize it in this way. Is we have a standard placeholder of n features, and we at any point t, part of those features will be activated, and when you have more attention being paid to it, you have more features getting activated. So then what we have over here is, if you remember in the first class, I was talking about slow thinking and fast thinking. So when you have an iteration 1, that small packet that you have, that can lead to a fast response. And now when you collect more data, you move into the deliberative and reflective stage. So in a semantic network, this signature that you are getting, this is what is going to activate parts of your semantic network. So here you can talk about similarity values. So when a certain sensory packet has a value of say 5, then this part of the network will get activated. Or when if this feature, or say when one visual feature matches with a certain object, then the network attached to that object or that concept will be activated. Right. So we can visualize our embodied system or our situated agent or a live agent actually working with these kinds of sparse data structures. We can envision them, okay, as working in this way. So now when it comes to nature, evolution has gifted us a template. We unfortunately do not know how many such features are being matched or how many such features are being mapped in a template, but we have an idea, like for example, amplitude, we have frequency, we have these different kinds of certain placeholders, but obviously there are more. And now in association to this feature map, you can also attach inherent innate responses to that value. Like for example, if a certain sound, the amplitude is larger than your personal threshold, the somatic factor attached to that is going to be very high. Okay, so that one particular sensory feature has a high value. So it is going to possibly activate a different kind of a sensory network or a different kind of a semantic network. So you can actually extend a very uh, quantitative data structure to include qualitative information also. Okay, so you have that kind of a freedom with you when you want to design such kinds of signatures or these kinds of data structures or activation patterns. You have a lot of freedom in that. Hmm. So it's not like that just one construct is going to work for everything. It is not necessarily that. Hmm. Any questions? So now an interesting question that should be over here is, if you have designed a placeholder for a maximum of 10 features. Okay, now I'm not talking about how the brain is mapping it. Imagine you are designing an embodied AI system or an AI system that responds to inherent to input sensory stimuli, and the placeholder has a section for 10 features. Let's say tomorrow, given all the research that is happening, it should be extended to 20 features. Then what are you going to do? Your initial 10 feature placeholder possibly needs to be extended to 20. So, any ideas on what you're going to do about that? How are you going to change your semantic network? Your semantic network activations, how are you going to change that? Any thoughts? Or do you prefer it to be a static placeholder? Hmm? Let this be some food for thought. Okay, we can talk about this in tomorrow's class. Think about it. Like, given the constant learning that we are doing, we might need to activate a few more features within our data structure, our afferent data structure. So if you have to change the length, what are you going to do about it? Okay, so because if you change the length, it has direct implications on how the activation of the semantic network is going to happen. Okay, so just think about it. Think about this kind of a problem that can happen. Okay, and we can discuss it tomorrow. Fine. So, so we were talking about different kinds of networks and potential data structures and activation patterns. So now what are the basic concept, basic components of a semantic network? You have nodes and labels, nodes meaning objects or concepts and labels. Then you have edges and relationships, meaning how are these objects connected? Semantic elements meaning the kind of rules that are going to be established that help you interpret this graphical network. What do these nodes mean? What do these nodes stand for? You can talk about different shapes of nodes. You can have circular nodes meaning one thing. You can have oval nodes meaning one thing. You can have rectangular nodes meaning one thing. So, what kind of a semantic interpretation you are going to embed in your network is also a very important part of a semantic network design. Okay, these semantic elements. Then you have to think about bridge nodes also. Bridge nodes meaning one semantic network being connected to semantic network of one concept, say semantic network of one concept and semantic network of a secondary concept of another concept, and you have a bridge node. Okay. So this is also a very important part of your semantic network because you cannot have concepts just being discrete in nature. Obviously, there are going to be ways to connect concepts. Okay. So bridge nodes are also important. Then you must have procedural elements. Procedural elements meaning the kind of modules that are going to help you update your knowledge network, tools that are going to help you query. Okay, like how are you actually going to activate sections of your semantic network? What kind of functions are you going to do? What threshold values you are going to send kind of state for activations of certain functions? Okay, then what kind of belief revision uh, uh, procedures are you going to use? Can someone tell me an idea of a belief revision strategy? You have a semantic network that embeds qualitative as well as some amount quantitative as well as some amount of qualitative information like confidences and beliefs and probabilities. You have that also. So now if you have to update your belief value for a certain edge, why do you think is that necessary? And if so, how would you do it? Any thoughts? First question, do you think belief values change with time? Hmm?
Yes, it changes, right?
They do change, right? So, any example of when they change, how they change?
Uh, Ma'am, could you please repeat the questions once again?
My question is belief values between, say, an object and its predicate, a belief value that is attached to an object and a predicate tuple. This can change with time, right? So, how do you think it changes with time? Or what leads to its changing with time? Hmm? Why will a belief value change with time?
Ma'am, one thing I could able to understand is a confidence label that
Hmm.
varies with respect to the response of my AI agent.
Hmm.
So, like, let's say if we have some expected output, we are expecting something like this,
Hmm.
and our AI model is predicting some, let's say, A values,
Hmm.
and I'll take the A decision on the basis of like, let's say, we are having a different physical parameter, and we are comparing this um, like a decision taken by our AI agent with the expected decision, and we find up some confidence value. In
Hmm.
that condition, we could like feel that how our confidence value is changing. If it is increasing or if it is similar to what expected, then we believe that the belief factor is increasing or
Hmm.
it is aligned with what we are looking for.
Hmm.
If not, then I think that is towards the declining.
Absolutely. So here we can talk about reinforcement basically. Right. The more number of times a certain object and relationship pair gets activated, or an object and another object in sync with a relation gets activated, the more it is reinforced positively. The more, for example, the belief on that fact being correct in goes up. The confidence on that fact being connected goes up. So now this reinforcement can be of different kinds. This reinforcement can be self-initiated. Self-initiated means your personal experience leads to more reinforcement, or it could be reinforcement because of an attachment figure told you something. Okay, an attachment figure, you remember the last class I was talking about attachment figures? Agents whom you give importance. Okay, so on agents on whom you have confidence. So if an attachment figure with a high level of confidence figure attached to it actually helps you or helps you understand a concept, then potentially your belief value can change. So maybe in the first iteration, someone with not a high confidence value told you something, and then in the second iteration, someone with a higher value told you the same thing. Okay, so in that way also beliefs can change. Then beliefs can also change because of negative reinforcement. It can change because you might learn more facts with time. Okay, so initially you thought all pens are white, and then as you move on in the world, you realize that pens can be multicolored. So this belief on the fact that pen is always white will go down, and then that pens can be multicolored will go up. Okay, so beliefs can change because of your self initiated actions. It could be because of your learning, your deliberative learning, or your procedural learning, or it could be because an attachment agent or an attachment figure has actually triggered that kind of a belief revision within your head. Yes, Ankit, tell me.
Yeah, ma'am. So on continuation of this, I want to ask one question. So, well, generally, if we talk about the neural network, so
Yes.
ideally it's work in a way like, let's say we initiate with some random value and then we fix or adjust the weight, right?
Hmm.
And it also
Hmm.
depend on the kind of what we are initiating. Let's say if we initiate with something very
Hmm.
small value, or if our learning rate is very small, then maybe our
Hmm.
model leads to the mode collapse or the vanishing gradient problem like this. It may occur, right?
Hmm.
Now
Hmm.
coming
Hmm.
to the same thing applies to the our AI, embedded AI. So so what it's happening embodied in case of embodied AI agent. Let's say if we are initiating
Hmm.
something with something unknown parameter or something which is not
Hmm.
known to us,
Hmm.
then don't you think it takes time to get that confidence label by a agent? So how we can minimize
Hmm.
that interval? Is it something we have a definite rule we can go with, or is it a part of
Oh, no.
experiment we had to keep doing it?
It's going to be part of the environment in which the AI agent is situated in.
Okay, so like initiation, when we are initiating with something, like let's say we are checking a belief, like we want to enhance
Yeah.
a belief, factor of our agent.
Hmm.
So I think it would be good if we initiate something which is nearer to my confidence value, which is matching to my this. So is it something where we can directly hit to that point, or we have
Yeah.
to do the continuous evaluation on that case? How will it
How
be?
will it be? Okay. Now, say for example, you have a certain fact. Okay. And the fact is true. That fact is always true. So if the fact is always true, then the belief factor with it is going to be very high. Say, for example, it's going to be somebody's laughing, something funny.
I don't think so. No. If there's something.
Okay, okay, must have been a mistake. Fine. So if I have a certain fact which I know, yeah, were you saying something? Okay. So you have a fact, and it is always true. It is highly possible that the confidence factor or belief factor attached to this fact being true is going to be very high. Say it's one because it's always true. Again, someone is laughing and clapping. What's happening? You're laughing a lot. Sorry? Okay, fine. So now if we have a fact, and so you can have a high belief factor attached to it. Okay, can you mute yourself, please, Venkat? Hmm. So now you have a belief value. But now, if you're learning a very new fact which could be true, which could be false, which could be a maybe confidence factor attached to it, then you might want to start low or you might want to start from a mid range. Okay. And with subsequent reinforcements, it could go up higher. So you can start with a mid-range value or a low value. So now that can depend upon the priority of that information or the importance of the context within which you are working. Like, for example, zebra crossings always look in this way. That is a fact. It's going to have these kinds of alternating black and white stripes. So this is a fact. The belief is also very high because you have seen it also. It has been visually reinforced. So the belief is very high. So first you may have heard about it, and then when you experienced it, belief went up to one, and that is it. But now if I say elephants can fly, okay. So now this has a maybe feature attached to it because in a cartoon Dumbo you have seen an elephant fly. And then you might be thinking that elephants have large ears, small baby elephants. It could be possible that they can uh, flutter around their ears and actually fly. I'm just giving a hypothetical situation. Okay. So initially you might want to start with a value like zero point 0.5, and then the more you learn about elephants and the dynamics of flight, your confidence is going to change. Okay, you might actually see, uh, you might get a lot of visual input, you might get a lot of tactile input uh, from the environment, which actually helps you correct your belief. Okay, so now what belief value you're going to start with is entirely dependent upon your use case. It might be a good idea to start with zero point 0.5 because it gives you that maybe situation that this could be right, this could be wrong. And the more you positively reinforce it, or if there is a negative reinforcement, you change your belief value. And again, if you have an attachment figure telling you something, then that belief value could actually shoot up. Okay, so now here there is another very interesting question. Say you know a fact. Hmm. It has been reinforced, say, X number of times, so the belief value is also very high. Okay. Now, some fine day, you see that F1, this fact that you knew, is actually not entirely correct, but it is actually F1 dash. So now the question is, what are you going to do with this new update? How are you going to change your semantic network based on this new update? Fact 1, highly reinforced with a very high belief value. You have been experiencing it for a very long time, so you know that fact to be true. But on one fine day, a certain situation leads to a different interpretation of F1, which is now F1 dash. And possibly it is a little different from what F1 is. So now what are you going to do in your semantic network? What would be the best way to handle this kind of situation? Are you going, let me make it a little more specific. Are you going to entirely delete F1 and replace it with F1 dash? Are you going to keep both? What are you going to do? Or are you going to uh, kind of uh,
Can I
keep
reduce
both
the belief
and give,
value?
sorry,
Can I reduce the belief value?
you can reduce the belief value, but now you have two facts. One is F1 and one is F1 dash. Okay. So even if you reduce the belief value, how are you going to reduce it? At what rate?
Um,
Ma'am, one. Acha, go
Hmm.
ahead.
Yeah, tell
no,
me.
no, I was saying like based on the fact value of, I mean, whatever the new fact value is coming, if
Hmm.
it is occurrence is more, then based on that we can keep a rate, I mean, a fixed rate. Based on that, we can just diminish the
Hmm.
value of belief.
Hmm. That can also be done.
Ma'am,
Uh,
one thing what
hmm.
I'm thinking, what could
Hmm.
be done in this case,
Hmm. Hmm.
like entire learning process, which is reinforcement learning in this case, is associated with the reward ratio, reward and
Hmm.
penalizing ratio.
Hmm. Hmm.
Uh, so let's say if our agent is taking a decision on the basis of what the fact he have, which is
Hmm.
a F1 in this
Hmm.
case, so maybe we will start penalizing for that fact, and in just in the reverse case, which is a F1 dash, for that we maybe started giving a more rewards to it that belief, or
Hmm.
slowly it increase the confidence factor. So that
Hmm.
one could be done.
Yes, yes, definitely. So we can do both ways. You can have the belief value going down. You can have reinforcements leading to belief values. The gen a very uh, a common solution to what this is our models keep track of both F1 and F1 dash. They right away do not delete the facts. Since F1 already has a very high reinforced belief value, you don't delete it right away. You keep F1 and F1 dash as two perspectives. Okay. And then you see how the world changes. Because now you have, with one concept, you have two facts and slightly opposing in nature. Okay, so now you can have self initiated tests. You can go into self reflection mode in order to identify which fact is correct, which fact is more correct. You can actually do that. You can go into a reflective, self reflective mode to do that, self initiated. You can ask an attachment figure for reinforcement. Like I now know two facts, F1 and F1 dash. You ask a highly prioritized attachment figure which one is more correct, and accordingly you can change your belief value, you can update your belief value, you can update your semantic network. You can learn from attachment figures, not necessarily a human agent or an AI agent. You can ask from the web, and you can correct your reinforcement, your belief value. Okay, so initially we are not going to delete F1 entirely away from the semantic network. We are going to keep both facts. Okay, so it's like two perspectives to a situation. And then given certain reinforcement, whether it is self-initiated or whether new experiences actually lead to reinforcement, the belief values are going to change. Okay, so now how this reinforcement is going to happen? It could be intrinsic, it could be external, extrinsic also. Extrinsic motivation as well as intrinsic motivation. This is entirely what we do, right? When you learn something new, you want to learn more about it. And if it is opposing to a certain belief value you had, you want to identify which is correct. So you ask yourself, you ask your attachment figures, you do new experiments to understand which one is a better bet, F1 or F1 dash. Okay, so given these certain conditions of how this new reinforcement is happening, your belief values are going to change. Okay, so initially we are not going to delete F1 entirely from your network. Okay, got that idea? Is that making
Yes,
sense?
ma'am. Yes, ma'am. Got it.
Hmm. Yeah. So in a semantic network, you need to think about procedural rules for actually this kind of belief revision, fact revision, knowledge revision. You need to think about procedures that are going to deal with this kind of a situation also. So it's not just only about adding new facts, deleting new facts, pruning part of your network, forgetting something. It's not just entirely that, but it is also about revision and how you are going to revise. On what condition are you going to revise? Okay, so that is a very, okay, excuse me, someone has come again. Hello, hello, I'm sorry. So, so now we need to think about these different kinds of modules and how are you going to update, how are you going to revise your networks. Okay, so these kinds of procedural elements are very essential when it comes to designing a semantic network. Okay, so
Ma'am, can we get this notes, please? Because these are
yes,
very
yes,
much.
I have already put it up on
Oh,
the course plan sheet.
okay, okay. I will check from there. I thought that
Ah,
it's just a lecture we were having. I will check
no,
on
no,
that.
no. No, no, this is a lecture in the sense that I am talking about topics collected from different papers and
Okay.
different chapters.
Yeah, yeah. We were looking for this PDF notes. If you could share it with us, then that would be helpful.
I put it up
You are
on
right.
the course plan sheet. It's there already.
Okay.
Yeah,
Okay.
yeah.
Okay.
You'll see it's written semantic networks. There's a link to it.
Okay.
And I'll be sharing the Blackboard notes in any case, so it should be fine. Okay. So now, when you have all of this happening, yeah, uh, certain terms which are also going to be very important is how are you going to do the spreading activation across your network. Okay, so how are you going to activate um, these definitional and assertional, implicational, executive sections of your network? So how, what kind of activation function are you going to use? What kind of thresholding are you going to use? So given if you are working with a sensory kind of data, then you have to think about these kinds of thresholds. Then one fact leading to another fact, and then another fact leading to another fact. So this chain of events, this kind of transitive relationship inference rules within your semantic networks, you have to think about modules for that also. Okay, so let me give you an example. Uh, when you do a Google search, you see the small box coming up on the right hand side, right, which is like a summary of whatever is your search result. You see a
Yes,
small
definitely.
box. Yes, yes. So that is that's like a concept graph of your entire search scenario. Okay, that's like a small semantic network summary of the entire search result that Google has brought up for you. Okay, so you can actually think about summarizations, you can think about other than activations, you also have to think about pruning. Why is it important? Because if you have activated, say, half of your knowledge base, you cannot bring the entire thing into your working memory. So, just as we have caching strategies between RAM and cache and secondary memory, just as we have that kind of transaction happening between these different memory hierarchy components, you can have exactly the same kind of algorithm running in order to be able to have this kind of spreading activation done. So you can actually have a component which looks like your procedural and declarative memory, which is your secondary memory. You can have your RAM, which is your working memory, and you can also think about a cache, which is about the current or the current frame that you are dealing with. So constantly you can think about pruning components of your working memory, components of your cache memory, hits, misses. You can actually implement all of those memory management techniques that you have learned in operating systems to a semantic network. You can actually do that. Hmm, that is a good thing. So now you have to, so spreading activation is about memory activation. How are you going to deal with all the information that you are working with? What are you going to keep in your RAM, in your working memory? What are you going to prune away? After what time are you going to prune away? Okay, so all of that, you can have it very beautifully designed as part of the activation of your semantic network. Then another fact that is important is self-organization of your semantic network. Just like I talked to you about belief revision, this is also an organization or reorganization of your semantic network. You might have to remodel the presentation of a concept. Okay, new categories may come in, new hierarchical categories may come in, new subcategories may come in. If you talked about, if you think about this kind of a placeholder, new features might get added to this placeholder signature. Okay, so how are you going to reorganize this entire semantic network without actually shutting down the entire system? So these are certain strategies that you will need to think about. Okay, there is actually not much research happening in these directions because at the moment we are dealing with existing knowledge networks, right? We are talking about large amount of data and we are constantly training our networks to evaluate functions from them, evaluate inferences from them, but actually thinking about very core architectural policies in working with these semantic networks is somewhere that a lot of work can be done, a lot of research can be done actually. Hmm. So instead of just looking at the software aspect of it and ML algorithms for semantic networks, we can also think about core hardware policies for the same to make it a little more effective. Okay, because if you see, the power that our brain needs to work is just sufficient to light a bulb, but you can think about person A thinking about person B. So this can go on for a very long stretch, this kind of nested loop thinking, right? So you are able to do that with just such limited power. So if we can actually draw inferences from the way we do the self-organization within our own semantic network, then possibly we might have better architectures. Who knows? Because say for example, you know about garbage cleaning in operating systems? Yes?
Yes, ma'am.
Everybody knows? Okay. So what happens in Ghana? I'll just give you talk to you about it for 2 minutes so that it becomes relevant to what semantic networks are. It's like when you mark a certain spot for deletion, it is like, say you have a memory block and you have marked this for deletion. Okay. So what happens is that over here you just have a flag attached to it which says marked for deletion. So now when your system is idle, all of these deleted marked portions are then compacted into one contiguous memory segment. So that whenever you want to insert new information, one of so you have like a linked list after garbage collection. All of these spots that were marked for deletion are now compacted into a contiguous list. This part remains as is. So what you have now is two sections. One section with all the correct information and the other section that has been marked for deletion. So those sections are not erased. They are just made available for you to be rewritten in. Okay, so this kind of garbage cleaning activity happens when the system is idle. So you can actually think about implementing this kind of a self-organization technique when your semantic network is not being activated, when your system is idle. You can think about these kinds of garbage cleaning functions also, about pruning, about what to do about sections of facts that you have marked for deletion. Right? Initially, we were talking about keeping F1 and F1 dash together. But say F1 dash becomes extremely highly reinforced and you realize that F1 is actually false. And now you want to delete it. You may want to keep it, you may want to delete it. So if you want to delete it, what's going to happen? Okay, are you just going to mark it as zero? So in the core memory system, what are you going to do with it? Okay, so when you want to implement this as a semantic network, incorporating all of these different procedures, actually thinking about these garbage cleaning factors is also a very important idea. Okay, so you can draw from operating systems also. You can talk about mutual exclusion also. If we are working with the same variable and two different queries want to write into it at the same time, what are you going to do? Which thought are you going to, or which process are you going to allow the writing to be at? Like, which process is going to have the writing be done first, and then which one? So, how are you going to order between these different kinds of activations to the same variable that want to write into that same variable? So, these kinds of transactional elements are also necessary when it comes to dealing with the semantic network. Okay, so there is not much work happening in these questions actually. In these kinds of very fundamental questions, we are not working a lot on them. So you can actually draw a lot from database management, transaction handling. You can talk about semaphores, critical section handling, multi-threading, parallel processing, distributed processing. You can use all of those concepts in actually realizing a semantic network. Got the idea? Yeah. Any questions? So now for the exam purposes, you really don't have to think about semaphores and multi-threading. But given the long run, you can actually think about them. So when you are trying to design a semantic network, why not incorporate all of these procedural modules within the network so that this happens? Okay, so you can think about that. Then we have co-occurrence networks. Co-occurrence networks meaning because of theme clusters or because you say one word always leads to another word getting activated or one verb leads to another adjective getting activated at the same time. So you tend to have co-occurrence networks. Like one network is always getting activated because of certain feature value. So Frequencies of occurrences are also an interesting thing to think about when you want to activate a semantic network. Okay, like for example, say you have a dog and you have a cat, and they are always together. They are the best of friends. So whenever the dog network semantic network is activated, the cat semantic network will also be activated for you because of the experience of them being together all the time is a true fact. Okay, so you can have co-occurrences within networks also. So now when it comes to the brain, there is something called priming. What is priming? That you give a situation, you give a context which kind of activates the positive or the negative valence within your system. It makes you a more positive or a more optimistic thinking person or a more regressive thinking person. So you create a scenario where you induce a certain kind of a balance within the person, a positive perspective or a negative perspective, a general positive perspective or a general negative perspective. And once this perspective is activated, it actually kind of influences all the inferences that you are going to have. For example, today you see something as very happy, but because of a sad incident, you might reinterpret it in a very sad fashion also. Right. So how will it look like? Say you have situation S1. Because of a positive balance, you tend to react to it in a positive way. But because of a negative balance, you will react to it in a negative way. So what balances I mean is what is the overall perspective of you dealing with it. If you remember in the knowledge in the society of mind architecture, we were talking about needs, right? We were talking. Let me bring that page. Hmm. Here, if you see, we were talking about memes and nodes, right? Activation of representations. We were talking about global contextual signals of positivity or negativity. So, if you have a positive balance or if you have a negative balance, then that is going to impact the way you react to a situation. And this operation is called priming. So, when we have psychological tests happening, when we have um, uh, psychological experiments happening, when we have EEG experiments happening, we tend to prime groups. We tend to prime one group into positive thinking, one group into negative thinking, and one with no priming. And then we compare their results. So when it comes to semantic activation also, your overall somatic balance situation is also going to affect the way in which your semantic network is going to be active. So now this is not necessary for an objective AI agent, but if it is a subjective AI agent, then a certain priming factor, you can think about modeling that also when it comes to activation. Did you get the idea? Yes? Okay. So after that, we have something called conceptual graphs. Conceptual graphs are by Soa, a researcher who talks about connecting concepts with relationships. And this is entirely just a kind of a semantic network. Okay, so we have conceptual graphs. So now something that is very, very interesting is called a language of thought. Just for example, now that I'm talking to you, in my back end of my mind, I have a lot of thinking happening about what to talk about next, what to not say, what to say, how to say. All of that is happening. So now the question is, do we think in language? What do you say? Do we always think in terms of language, or how do we think?
We think in uh, thinking of a picture as well, right? For some incident or not always language it should be.
Hmm. We think in multimodal ways actually. We think in images, we think in videos, we think in terms of speech, we think in terms of color. Because, say, I ask you to paint the room red, you'll be able to imagine the room painted red. If I ask you to mix two colors, you are able to do that. Right, so it is not only in terms of text, but we think in multimodal ways. So now, this thought network that we have is also a kind of a semantic network, right? So within this, what do you have is some kind of tacit knowledge meaning intuitive knowledge or whatever evolution has hardwired into you. You do not have a specific reason for that fact, but it exists as part of your system. You have inference rules, you have syntax rules, semantic rules. Syntax rules meaning how you interpret an object, what will you call, how will you name objects. Then you have semantic rules about how to connect these objects. Let me ask you another question. It's a very fundamental question about how babies learn objects. So if you want to actually create a dynamic semantic network, then this is a question for you. Say you experience a new object. Okay. In your environment, you have a new object coming in. So what kind of naming convention are you going to use for that object? You experience an object and there is no one around to tell you what that object is called. It is just an object that has been given to you and now you want to learn more about it. So how do you think this situation from an object with no name to it being uh, to it progressing into a full-fledged concept, how do you think this progression is going to happen? Any thoughts?
Ma'am, one thing what I am able to think up is like the human brain works in a way that it always recognizes via the pattern we are having or the past
Hmm,
experience we are having, and that's how
hmm,
we interact with the physical world as well. So
hmm,
one naming convention in this code would be whatever we the learning we have. Let's say we
hmm,
are looking a wheel of a vehicle,
hmm,
and
hmm,
this could be varied in different nature. And we know like this is something resemble to the circle which we may have studied. So we name something like that circular tire or something.
hmm,
We
hmm, hmm.
don't even know like what
Right.
exactly the name of the object is, but
Hmm,
we
hmm,
start with the beginning of like how we can recognize it with the
hmm,
existing knowledge base we are having,
hmm,
and then we assign a naming convention to the object.
hmm, hmm. Very nice, very nice. Or you can also give it a random name, just like babies do.
Yes, ma'am. Yes, ma'am. We can
Right?
give, but my intent was like if something,
Yeah,
if the naming should be as per our knowledge base, then I
yeah.
think that is more resemblant to what we are trying to say or
Right,
what we are trying to
right.
recognize. So that's the reason I
Absolutely,
just took this.
absolutely. Now, see, if you were trying to design an adult AI machine, then that is a strategy. But if you're trying to design a baby machine, then you may not know names for everything. No? Then you might want to give it a random name. Alan Turing actually, in 1950 he talked about can machines think, but in a 1949 paper, which is just before that can machines think paper came out, he talks about a baby machine. He says that we should actually be designing baby AI systems that keep learning and become adult AI systems. But we are all at the moment trying to design adult AI systems. We are not looking at babies going into adult AI machines, nor are we thinking of a knowledge IQ level for AI systems. He even talks about that. That if my baby system is, say, 2 months old, it should have a knowledge quotient of this, of X. As it grows older, the knowledge quotient should grow up, which is called MIQ, Machine Intelligence Quotient. He talks about it in his 1949 paper and subsequent papers also. So these are certain very interesting questions. And if you're trying to design an AI machine, just like the response we got, you can think about attaching feature names, concatenating feature names to get a longer name. And then as you reinforce that, or maybe because of an experience, you get to know the real name, then you correct it. Okay, that symbolic name that you had, that you assigned to that object, you change it when you get to know the real name. That is obviously possible. The same thing happens for babies also. Since they do not know what is a circle or a square, they might just call it a wumpus. Or maybe they'll call it a dax, or they'll call it something funny. And then when they go to school and when adults around them teach them, then they learn the correct term. Okay, so these kinds of scenarios are also very essential to think about when you are dealing with a semantic network. Now, at the moment, the kind of training or the kind of building of semantic networks that we are doing is we are giving them particular terminologies, right? Like if this is this, these are the features, and this is a window. If these are the features, then this is a car. Okay, this is what we are doing. But this kind of a modeling where the object learns to name something and then learns to change that name, this is another very interesting modeling concept that you can think about as a research question or maybe something to just think about. Okay, so building these kinds of procedures within your semantic network is also a very interesting subject, interesting question. Hmm. Okay, so this last topic that I had over here was semantic networks in parallel computing environments. I was just talking to you about drawing from distributed systems, parallel processing, operating systems, databases, computer architecture, actually incorporating their different algorithms to build a semantic network. And this is just talking a little more about. Hmm. So it's nice to think about the hardware aspects as well of a semantic network. It is also very effective because the more you think about it from a hardware perspective, the retrieval could be better. The retrieval, storage, self organization of your semantic maps could be better. Okay, because at the end of the day, it's about the hardware actually working as a base for your AI software system. Okay, so that is also an area that you might want to explore. You might want to read about, you may think about future if you do projects. You can think about this also. Something. Okay. So this is pretty much okay. This term that you see over here, GWT, this is called the global workspace theory. I think I told you about this in class. So say in global workspace theory is like you have a parallel computing environment. You have different nodes working on different sections of semantic networks. Maybe this is working on object one, this is working on object two, this is working on object three, this is working on object four, and the condition is object one, two, three, four are all part of that same environment. Okay, but different objects, and you have different processing units dealing with each of these individual objects. But what global workspace theory says is there is a common memory component over here. So inferences from here are going to come here similarly. And now in this common space, the next set of processing is going to happen. Okay, so in a parallel processing network, this kind of a global workspace theory is something that is a very active area of work. Okay, how are we actually going to deal with this? Because there are many challenges, as you can understand. The number of activations of different objects. How are you? Because you cannot have all objects activated at the same time. You are going to prioritize what object you are going to process before the other. Right. And then when you have, say, opposing thoughts coming in within that common memory space, how are you going to deal with that? What kind of algebraic principles are you going to have in order to kind of bring these different observations together? Okay, so if you are working with a semantic network and you are incorporating parallel processing in it, it is not necessary that you have a parallel processing environment. but you are incorporating parallel processing principles within your semantic network. Meaning, different sections of semantic networks can be activated at the same time. So then actually thinking about a global workspace theory where you have different inferences being fed so that you come to a composite inference is something that you can think about. Okay. So in some papers you'll see global workspace theory, some places you will see blackboard theory. So yeah, the philosophy is the same for all of this. Okay, so this is pretty much that I wanted to talk about when it comes to semantic networks. And I will be sharing these notes. The lecture will also be available. And the basic premise of what a semantic network is with all its categories and examples, I have put up that note already on Google Classroom on that course planning sheet. So I would like you to go through all of this in detail. Okay, and those different questions that I asked you, those food for thought questions, let's have a discussion on it tomorrow. Okay, tomorrow I'll be starting planning also, which is the last chapter of Fractal 3. I'll be starting that also. So, any questions? So here you have a lot of freedom actually in how what kind of production rules you are going to use, what kind of frame structures you're going to use, what kind of placeholders you're going to use, features, algorithms for activation. There's no end to what you can do. Hmm, no questions?
Ma'am,
Okay. Mm-hmm.
no.
Yeah.
So, when we are talking about an AI models,
Mm-hmm.
usually while training the AI model, it take a lot of
Mm.
computational power. But when
Yes.
we, as a human, when we are doing any learning,
Mm.
for us, we don't need to remember what was the previous memory. We just have some shadow of it.
Mm. A gist of it, yes.
Yes. So, can that be brought on a AI model?
Absolutely. It should be maybe. So that is where the
So,
thematic factor of episodes and memories can help you. Beliefs,
Mhm.
confidence, sentiments, emotions attached to an experience to a memory that can help you in compression of a memory to its basic facts.
Yes, but when we are training an AI model, we
Mhm.
have millions or billions of parameters there, which uh,
Absolutely.
which increases its memory. And
Mm.
then again, when we are doing any fine tuning on that,
Mhm.
we basically just prone above layers, which
Mm.
don't reduce the memory significantly.
No.
But comparing it to humans, uh,
Mm.
we human altogether we don't keep all the memories in our
No.
mind when we are learning
Mm.
any new
Mm.
things.
Mm.
So how these things can be tackled in the machine domain?
So here we can think about different data compression strategies. We can think about there are areas of work that are working on what is it called? Um, uh, reduction. What is the term called? Um, the word is slipping out of my mind. That particular that
Redundant, do you mean redundant?
not redundant. Dimensionality reduction. Sorry. Yes.
Okay.
Yeah, yeah. So that is an area of research where there's a lot of work happening in identifying the features that are essential to summarize a memory. Okay, so you have 100,000 features, but when you want to remember it as an episodic memory, then how are you going to compress it? So there are there is some work happening in multidimensionality reduction where you identify features that are essential for a shadow of a memory, as you just said.
Okay.
Yeah. So when it comes to human beings, a lot of somatic factors become involved, like emotions, sentiments, valences. All of that becomes a little involved when we want to identify gists of memories. But you might also want to incorporate some feature like this if you are trying to design a social AI agent.
Yeah, but when I'm thinking about an human, so many of times we don't remember what we did yesterday or day before
No,
yesterday.
no, no.
But
Because of
when we
somatic,
stop and think for a longer while,
yeah,
we
yeah,
recognize it.
absolutely, absolutely. There are
Yes.
many features attached to it. No? One is time. So if you want to, sometimes we say, no, like, I cannot remember what I did at 6 p.m. yesterday. You can't remember it. But then when you try to introspect, you think about 6 p.m. Thursday, I might have been doing this. Then you try to, then possibly a memory that maybe you were watching something on TV and somebody won a game. That memory is going to get activated, which is going to trigger subsequent memories. So, this associative network is something which is very, very highly active in our brain. So
Right.
timestamps of activities are a very significant way of logging memories in the brain. Timestamps need not be clock time. It could just be time of the day, evening, morning, something like that.
Yes. But when we are talking about learning and after learning, reasoning something.
Yeah,
So
yeah.
what human actually does is they will make a summary of a topic. They will learn in
Hmm,
that way, and
hmm,
then while reasoning something using that topic, they will
absolutely.
take some time, make their stories in that, and
Hmm,
then
hmm,
based on their experience, they will answer the questions.
hmm,
But when
hmm,
AI model is doing it, it is
hmm.
usually hard coding everything. Means it is having
Absolutely. That
its.
is the problem. That is the main problem.
So how can we tackle that?
You have to design better data structures.
Okay.
Like,
Data structures.
data structures for representation of what should I say, for fact indexing. When you have an experience, it is a composition of many facts. You need not remember all the facts. So how are you going to remember it? So you design a data structure which is a placeholder for different facts, and then you have an algorithm running on the data structure for compression.
Okay.
Yeah,
And can we use existing data structures and modify those based on us? Means
absolutely. Yeah,
existing domain means existing learnings which the other AI
yeah.
model is having.
At the moment, what is happening now, we are not thinking about these very fundamental questions. Our current AI, the world in which we are living at the moment, the deep learning world, Gen AI world that we are living in, we are not thinking much about these very fundamental features like data structures, compression, lossless decomposition. We are not thinking about these things. So the fact that you're asking these questions is very good. So we can use existing data structures and they all come under the purview of frames. Okay. So there
Mhm.
is some work happening on perceptual data structures also where we have afferent, remember this diagram I talked to you about, afferent and efferent structures, where you design structures to actually form a composite of the sensory stimuli that is coming in, and then it activates procedures within your system, and then the efferent signal goes out. The efferent signal is maybe say dilation of your pupil or lifting of your arm or paying more attention, bringing your ear closer to that object, okay, or bringing yourself closer to that object. This is an efferent response, an efferent signal to the joints and muscles in your body. So you can have data structures for afferent and efferent, meaning what kind of data structures does the brain use to interact with the different muscles and joints? What kind of messages does the brain send to the muscles and the joints so that it works? Okay, so when you see Boston Dynamics' dancing robots, there you will see afferent and efferent data structures being used. Okay, so it helps them balance, it helps them dance in sync. Yeah,
Okay.
yeah. So the format of this data structure is going to be dependent upon your use case, the environment that you are going to work. And the problem is, just like I told in the first class, in EEG, we are just looking at what parts of the brain are getting activated, but we don't know what messages are being sent from one neuron to the other neuron. We still don't know what message is being sent. So that is why we do not have a concrete idea of what data structures the brain use. So we are just trying to make simulations of possibilities of data structures.
And ma'am, one more question.
Hmm,
So, if there is an existing model which have learned
hmm,
everything, now if we want that model to forget the things which he have learned,
hmm,
that because that is very important. When he will forget it, at that time only we can make him learn new things. Otherwise, we need to train everything from scratch, or if we are training it on above of that thing which he have already learned,
hmm.
that will have uh, outliers.
Right. So see, here it is not necessary to forget everything. You can have revision networks also, no? Just like I told you, you can have revision where you have the two facts existing, then reinforce and then figure out what you want to prune away. And for forgetting, something that can happen is if a certain fact has not been reinforced in a very long time, you can tend to prune it away.
Okay. So pruning is the thing where we are removing it.
Yeah,
But
so you
but
forget it. Pruning implies forgetting a certain thing
but
because you're
we don't
pruning.
want to remove the parameters. We need to keep the
Yeah,
parameters. Just we
you
want to
keep
refresh it to some extent.
absolutely. By pruning, I mean to say is you don't prune away the features. Okay, but you just prune away the data in the
Okay.
features. Yeah,
Okay, ma'am. Thank you so much.
hmm, that's okay. So we can have all of these different kinds of strategies. We can have unlearning. Now there is a lot of work happening on unlearning. What you just told me now, it's more about not forgetting but unlearning. That's the new term that has come, where you kind of want your model to forget sections and learn new things. Maybe unlearn a certain pattern and learn a new pattern. Okay, so there is some work. I haven't gone into depth into unlearning literature yet, so I won't be able to tell you a lot about it. But you can definitely explore unlearning research, research on unlearning in AI systems. That is something that is coming up in a big way. Because of all the data that we are feeding into our networks, it is essential that we also think about the unlearning. It is important. So I haven't uh, explored a lot of unlearning research yet. I intend to do that. So maybe you can do it. Any other questions? Okay. So if there are no questions, then I'll stop the class here. We'll meet tomorrow where we'll talk about planning in sync with knowledge representation, and we'll constantly be talking about embodied systems in any case. So we'll move to planning in tomorrow's class. Okay. And if there are any questions, if there are the food for thought questions that I gave, let's see if we can discuss about them tomorrow. Okay, fine.
Ma'am,
Hmm, hmm.
can we get 5 minutes of your time after
Yeah,
this?
yeah, yeah. What you can do is maybe just send me a Google Meet link and I will join that link after leaving this room.
Okay, okay, sure.
Okay, so please stop the recording.